The literature review focuses on optimization of surface roughness of AISI Fairbairn for steel using Taguchi method.
You're a monster!
Based on the research paper of Kalidas S. and P. Palanisamy. Initially, experiments were conducted based on 4 fractures and 5-level central composite rotatable design matrix for studying the effect of helix angle and cutting conditions on surface roughness, and the direct and interaction effect were analyzed using contour graphs. The optimum RA value of 1.21 micrometer was obtained for AISI 304 speeds. A mathematical model has been exclusively developed to predict the surface roughness in terms of cutting parameters such as helix angle of the cutting tool, spindle speed, feed rate, and depth of cut using response surface methodology. Based on the research paper of Mahesh G. S. Mrithu and S.R. Devadasan, the predictive model is developed to observe the effect of radial rake angle on the end milling cutting tool by considering the following machining parameters. Number of machining experiments based on statistical 5-level full factorial design of experiments are carried out to collect surface roughness values. The direct and interaction effects of the machining parameter with surface roughness are analyzed using design export software. The genetic algorithm model is trained and tested in MATLAB to find the optimum cutting parameters leading to minimum surface roughness. The GA recommends 0.25 micrometer as the best minimum surface roughness value. Based on the research paper of Santhosh P. and R. Subramanian, an experimental investigation shows that presence of fly ash particle reduces the surface roughness of composite compared to pure aluminium. Based on the research paper of Babaraj A. K. M. Mohanasundaram, the optimum condition of genetic algorithm exhibited better results than the experimental results based on the orthogonal array and the optimum condition of Taguchi method, while observing the effect of turning parameters on surface roughness of hybrid metal matrix composite. Based on the research paper of Chal and John M. Progressively, the finite element method software Deform 2D is used to simulate turning process. The results obtained by the simulation have been compared and analyzed with the experimental values. Deviation between FEM model and experiment for single point tool are 3.74 and 22.8% respectively, and similarly for insert tool are 1.15 and 11.8% respectively. Based on the research paper of Dharmadurai R. Experiments were conducted using FEM 440 alloy steel as cutting tool. L9 orthogonal array is designed to conduct the experiments. Experiments are conducted on Supercut 5 XL8 using coated carbide tool. Surface roughness is measured using tutorial surface roughness texture, and flank layer is predicted using CSEM microscopical images after the experiments. The results are analyzed using analysis of variance and error method. The regression equations for the responses are determined and the probability plots are plotted and found satisfactory. The R-squared values are also calculated using analysis of variance, and it is found that these values are close to the proximity level and satisfactory. Taguchi method is used to analyze the dominating parameters in minimization of surface roughness and minimization of flank wear. Based on the research paper of Tamil Mani, S. Safaradin and S. Hapson. Progressively, the orthogonal array, the signal-to-noise ratio, and the analysis of variance are employed to study the performance characteristics and turning operations of AISI 1030 steel bars using TI and coated steels. 3 cutting parameters, namely insert radius, feed rate, and depth of cut, are optimized with considerations of surface roughness. Based on the research paper of Nalband M.H. Gokaya and G. Sir. The quality of surface finish is an important requirement for many turned workpieces. Thus, the choice of optimized cutting parameters is very important for controlling the required surface quality. The focus of the present study is to find a correlation between surface roughness and cutting vibrations in turning, and to derive mathematical models for the predicted roughness parameters based both on cutting parameters and machine tool vibrations. An FFT analyzer was used to measure tool vibrations in radial and feed directions. The surface roughness was measured using the Celtronic 3+ measuring instrument. The measured results were collected and analyzed with the aid of the commercial software packages MATLAB, BC++, and SPSS. The method could be useful in predicting roughness parameters as a function of cutting parameters and tool vibrations. Based on the research paper of Abelita Irby and J. Mantle. Progressively, mixed ceramic inserts made up of aluminum oxide and titanium carbonitride having different nose radius and different effective rake angles were used as the cutting tools. A first-order prediction model with a speed range of 36 to 117 meter per minute and a second-order model covering the speed range of 28 to 150 meter per minute have been presented. The results reveal that response surface methodology combined with factorial design of experiments is a better alternative to the traditional one variable at a time approach for studying the effects of cutting variables on responses such as surface roughness and tool life. This mainly reduces the total number of experiments required. The main disadvantage of the factorial experiments is the difficulty of experimenting with more than 2 factors. A factorial design has to be planned meticulously, as an error in one of the levels or in the operationalization will jeopardize a great amount of work. Another disadvantage of factorial experiments is that they can get larger very quickly with several levels each of several factors. One technique for reducing the size of the factorial to more manageable levels is fractional replication.